Okay, so we're finishing up our discussion about logarithmic differentiation, and I just wanted to make a couple of points here. So because the log of a to the b is equal to b times the natural log of a, logs change exponentiation, that's a big word, exponentiation into products. Right? Instead of having a to the b power, it's b times the natural log of a. And the second nice thing about logarithms is that when you take a product, it turns into a sum. And so logs change products, or quotients you could say, into a sum or difference. Okay, and so this is why these two properties right here are the reason why logarithmic differentiation works. Okay, so if you're trying to differentiate something that's a big product, right, like in the last example, we had this product of this function with this function, and so instead of dealing with that, once we took the logarithm, we were able to break it into a sum, and furthermore, the exponents just drop down in front as constants, and so presumably then, after you've taken the log, this would be a lot easier to differentiate, right, than this. Okay, so that's the idea. And so up to this point, we've really had a choice as to whether to use logarithms or not. And so the one question might be, is there an example where you're forced to use logarithms to differentiate? And the answer is, I guess I better write down the question first. When are we forced to use logs before differentiating? And the answer is, when you have something of the form y equals f of x to the g of x power. Okay, so that means you have a variable in the base and a variable in the exponent. Let's see why. So we'll do an example and then we'll look at the general case. Example, y equals x to the x, find y prime. Okay, so again, the very first thing you do is to take the log of both sides. And the reason we do that is because the right hand side changes from exponentiation into a product. And now we know how to, we know how to differentiate a product. Okay, so now we differentiate and we get 1 over y dy over dx. That's the implicit derivative, right, of the natural log of y, equals, and now we're taking the product rule of that. So that's going to be the natural log of x plus x times 1 over x. And so that's going to be, so remember we just did the derivative of the natural log, right? And so that's the natural log of x plus 1. But wait, we're not finished. The last step is to solve for dy over dx. And so we have to multiply both sides by y. Natural log of x plus 1. Okay, but you don't want to leave your answer in terms of y. We want our answer in terms of x. So y is equal to x to the x. So we get x to the x times the natural log of x plus 1. Very good. And so this is the derivative right here. This is the derivative of x to the x. Good. So now, the general case of why this works. And again, don't memorize the final answer for this, but you want to memorize the technique. So if we're given f of x to the g of x power, we take the log of both sides. And again, the reason is because exponentiation changes into a product, right? And so now we have a product of two functions that we can differentiate, and so therefore we differentiate. So dy over, oops, I forgot my 1 over y. Don't forget that. That's the derivative of the natural log of y. That's going to be g prime of x times the natural log of f of x plus g of x times the derivative of the natural log of f of x, and that's 1 over f of x times f prime of x. You could put the f prime up on top. Good. And so then you would go ahead and multiply both sides by y. So you'd have y times g prime of x natural log of f of x plus g of x. Lots of writing, but I think you see what's happening here. And so finally we would write that the derivative is equal to f of x to the g of x power, so you're rewriting your y, right? And then times this whole expression, g prime of x times the natural log of f of x. Here, I'm going to pause while I write this. Okay, so I finished writing that, and that is your answer. Good. Now, my final word for the video is a caution. Caution. Beware of the difference between a to the f of x power, f of x to the a power, and f of x to the g of x power, right? So in this case, the base is constant. You have a constant raised to a variable power. Here you have a variable raised to a constant, but here you have a variable raised to a variable power. Okay? So how do we differentiate each of these cases? So if y is equal to a to the f of x power, then the derivative is the chain rule, and so the derivative of a to some power is a to this some power times the natural log of a. Then we multiply by the derivative of the inside function, so that's going to be times f prime of x. Okay, so that's the first derivative. The next one is if you have f of x to the a power, then what's the derivative? Well, now you can use the power rule, so that would be a times f of x to the a minus 1. Then you want to multiply by your f prime of x. Good. And lastly is the one, whoops, sorry about that. Lastly is the one that we just did. If y equals f of x to the g of x power, then what we want to do is logarithmic differentiation. So your first step, like I said, is to take the log of both sides. Natural log of f of x to the g of x power, which brings the g of x down in front. Okay, and then you differentiate as usual. Good. So that is the logarithmic differentiation. Logarithmic differentiation. Should we try one more just for fun? I think we got enough time. Okay, I'm going to pause this while I write down the question. Okay, so here's a function. It's a triple product, so that might be harder to do. How should we approach that? Well, of course, we're in the section on logarithmic differentiation, so everything is logarithmic differentiation. But the reason is because what happens when you take the log of both sides? Well, like we were saying, if you have a product, it becomes a sum, and the exponents become products. So this is going to end up being 1/2 times the natural log of x. Oh, maybe I'm going to pause this while I write down the logarithm of the left-hand side, or the right-hand side. Okay, so here I've written the logarithm and broken out the product as a sum. Okay, and now we want to rewrite each of these exponents here, right, by bringing them down front. So I'll pause again while I do that. Alright, and so I've just brought forward brought the powers down front, right? So this is x to the 1/2 power, the 1/2 goes in front. Good. And now, by the way, natural log of e is equal to what? Oops. Natural log of e is equal to 1. So we can simplify that even further. And so now if we differentiate, we'll have 1 over y prime is equal to 1/2 times 1 over x plus, that's just going to be 2x minus 1, plus, that's just going to be 2/3 times 1 over x plus 1. Wow, that was easy. And so y prime is equal to this big mess. Let's see how fast I can write it so you're not having to watch me. Okay, there's your original function. That's your y times your derivative 1 over 2x plus 2x minus 1 plus 2 over 3. I guess you could write it this way. Good, and there it is. That is logarithmic differentiation. Now notice again in this case that we actually had a choice of whether we wanted to use logarithmic differentiation or not. Some cases, like this first case we had, where is it? There it is. Oh geez, that was a while ago, wasn't it? In this situation, you really don't have any choice whether to use logarithmic differentiation or not. So that means you have to. Alright, so that's it for logarithmic differentiation and the derivatives of the logs, section 3.6.